Okay, good morning, everyone. Morning. Hope you guys had a good reading break. I'm surprised that there are this many here when it's been snowing, but that's good to see. As we're just coming back from reading break, today is a nice, easy review lecture. So we're just reviewing one-dimensional ordinary differential equations, or ODEs. So hopefully this should be fairly familiar to you guys. It's covered in 154. So most of you should have this fairly recently in your memory. So we're going to go through some problems today related to one-dimensional ODEs. This is in prep for taking this into multiple dimensions, as is the theme for this course. So we're going to start on Wednesday looking at linear systems of ordinary differential equations. And then next week, we'll go on to nonlinear systems. Okay, so just before we get started, I guess, in terms of like differential equations, why do we care about them? With differential equations, especially ordinary differential equations, are quite like the bedrock of a lot of mathematical modeling. And that's true whether it's in biology or physics, engineering, chemistry. They tell us essentially about rates of change. So if you're doing, say, biological models and you're interested in predation rates in a predator-prey population, they can tell you about the rates of change in terms of population growth. They can tell you about the rates of change in terms of disease models. So how quickly are people getting infected, how many people are getting infected, how are they recovering. So they're really useful across lots of different scenarios. And up until now, you've only met them in one dimension. So if you've got a very simple population model, say some bacteria or human population growth, and you just want to say, okay, what's the total number of individuals in that population? How's that changing over time? We can do that using one-dimensional ODEs. Okay, so that's pretty straightforward. But as soon as you start to introduce any sort of heterogeneity or structure into those populations, then you need to think about systems of ODEs, and that's what we'll be building up to. Okay. So examples of systems of ODEs, well, I mentioned diseases, so epidemiological models where you have populations structured into those who are susceptible and uninfected, those who are infected, those who are recovered. You might have age-structured populations, so juveniles and adults. You might have populations structured into males and females, or individuals who are high risk and low risk. So there are lots of different ways in which you might want to structure populations, in which case systems of differential equations is how you need to approach these problems. Okay, but for today, we're just going to be focusing on those one-dimensional population models and just recapping especially some of the graphical methods that we can use to look at them. So this used to be, this review used to actually be 2 lectures, but I felt that was too long. So there are 2 sets of problems and there were 2 pre-lectures. I'm just going to go through part 2 of the problems today. The solutions to part 1 are online in case you need some additional practice, okay? But the exams won't contain anything on one-dimensional ODEs, okay? This is really just there to make sure you guys remember how to approach them before we go on to the 2-dimensional stuff. Okay, so what does an ODE look like? It looks something like this if we just have one variable. So for example, the p dt is equal to some constant r times by p. And this is known as an exponential growth model. This is pretty much the simplest model we can have. The kinds of questions we want to ask whenever we're looking at systems or single ODEs is, are there any fixed points or equilibrium or steady states? These essentially mean the same thing as far as you guys are concerned. So these are points where the population is no longer changing. Can we find them and can we tell something about their stability? Okay, so these are the kind of questions that we tend to ask. So the pre-lecture went through the logistic model. This is a very classic model. It tells you the population growth for many different types of organisms. So human population hasn't reached our saturation point, but typically you see exponential growth when in many populations when there are lots of resources to begin with. And then eventually these things saturate. So a classic population curve for many populations has this S shape like this. We have some sort of exponential growth early on when you've got resources not being limited. Then you've got this strong phase of growth in the middle where the population is really increasing quite rapidly. But as it gets to very high levels, the population saturates, okay? And so this is probably what we'll see with the human population as well. We'll saturate at some point later this century. You see it in bacteria, if you've got them in a Petri dish. You can see all these sorts of S-shaped curves pretty much throughout nature. So you can model this using a very simple population model like this. And this is an N here, but we can think this is our P. And one of the powerful ways in which we can analyze these models, we can do some algebraic analysis, but we can also do graphical analysis like this. So if we plot that growth function, this R of P, this is our per capita growth rate. So when we say per capita growth rates, we're talking about the rate of change per individual in the population. So per capita means per individual. So this is the per capita growth rate at population size P. If we plot that, we can see as P increases, this per capita growth rate decreases. And you can kind of see this on this graph to the right-hand side here, that the per capita growth rate is very large when P is small, but when P is large, it gets smaller and eventually tends towards zero. This is important because it tells us here when it crosses zero, there's no change in the growth rate. Okay, so when R of P is equal to zero, there's no change in population size. Therefore, you have what's called a fixed point or a steady state. Okay, so we can go on and do some more graphical analysis here. If we plot the right-hand side of our function, so if we have dn dt is equal to some function g of n, we can plot what that g of n, that growth rate function, so this time not the per capita growth rate, but the growth rate for however many individuals there are in the population. We could plot that, and then that tells us something about whether the population is increasing or decreasing. If this curve is above the axis, that means that dn dt here is positive, so the population grows. If it's below the axis, then it's negative, so the population shrinks. And when it's equal to zero, it's neither shrinking nor increasing. Okay. We can then look at the sign of this function, the gradient. If it's positive, that turns out to be an unstable equilibrium or an unstable fixed point. That means that if we start near that point, we move away from it. And if the gradient of this function is negative, then we have a stable fixed point. So one way of thinking about this is to think about hills and valleys. And if you think about a ball that's on top of a hill, this is an unstable equilibrium, okay? Because if I nudge this ball a little bit to the left or a little bit to the right, it's going to roll down the hill. It's going to move away from equilibrium, okay? So that's an unstable equilibrium, whereas a stable one is a bit like a valley. So if I have a ball in this valley here, and I nudge it to the left or nudge it to the right, it's going to move back to where it started, okay? So that's really the way of thinking about stable and unstable fixed points or equilibria. Unstable ones, if you move a little bit away from it, a small perturbation, you keep moving away. If it's stable, if you move away from it, you come back to it, okay? Okay, the pre-lecture also went through things about Allee effects, which I won't go through now, but that's quite important when it comes to conservation and fishing, because essentially if you reduce a population below a particular threshold, it can die out, okay? So it can't recover. Okay, there's a section about linear stability of fixed points, which is what we're going to talk about a lot over the next couple of weeks. You don't need to know how to derive these Taylor series. This is here for background to emphasize where it comes from. This is really quite similar to what we did when we looked at linear approximations, here just in one dimension. If you've got a curve and you zoom in enough, everything basically looks linear, and that's essentially what we're doing here again. We're ignoring these higher order terms and just saying, okay, if we move a tiny bit away from our equilibria, do we move away, do we come back? And that's quite powerful, especially when it comes to systems of ODEs, because we can look at these linear systems and use the tools that we use in those linear systems when we do our more complicated nonlinear systems. Okay. That is all I'm going to go through from the pre-lecture material before we go into some problems. Does anyone have any questions? Nope. Okay, let's do some problems. Okay, I'll go through this first one with you and then get you guys to have a go at practicing. So here we've got some one-dimensional ODE. You can imagine this as a population Y, or it's describing some biological problem. Typically, we're going to be talking about populations, but they're not always populations. It could be things like a position in space. It could be something different. But here, we can just imagine that they're populations. Okay, so we've got a population Y. Its growth rate is y squared minus y, so dy dt is equal to y squared minus y. The first thing I'm going to do is I'm just going to refer to this as g of y. Okay, just some function g of y, just because it will make the notation a little bit easier. And here we want to identify the equilibria and determine whether they're stable or unstable. Okay. So how do we work out our equilibria? Can anyone remember? Yep. Exactly. So we set this right-hand side to 0, okay? Because if dy dt is equal to 0, that means that the population is neither increasing nor decreasing, it's stable, okay? So we want to look at when g of y is equal to 0. So that's just the same as setting y squared minus y, that should be a 1. Y squared minus y is equal to 0. Okay, we can factor out one of the y's here. So if y times by y minus 1 is equal to 0. And then because we're taking the product of these things, this tells me that either y has to equal 0 or y has to equal 1. If y is 0, then this first term is 0. If y is 1, this term is 0. The product of these things is then 0. So we have our two equilibria, y is equal to 0 and y is equal to 1. Now we want to work out their stability. So to work out their stability, we need to think about the derivative of this growth function, g of y. So if we take the derivative of g with respect to y, we're just going to get 2y minus 1. So we had y squared, so that becomes 2y when we take this derivative. We had a minus y, so that's minus 1. When we take this derivative. Okay, so we've got my equilibria and I've got this general growth function here. How do I work out the stability of those equilibria now? Any ideas? Yep. Exactly, we just plug them in. Okay, so let's take this y as 0 first of all. So g prime of 0 is going to be 2 times by 0 minus 1. So that's minus 1, which is less than 0. Let's do the same for the other one, and then think about what they actually mean. So g prime of 1 is 2 times by 1 minus 1, which is equal to 1, which is greater than 0. So we don't actually care about what their values are here. We care about their sign. So let's think about what this actually looks like if we were to plot it. I'm going to zoom in over here. So if we plot our growth function, g of y, remember this is y squared minus y. We know that it goes through 0 and 1 because those are our equilibria. So it crosses the axis here at 0 and 1, and it's a quadratic that looks like this. So this is 0, and this is 1. These are the points where it crosses the axes. And I've just worked out my g prime. It's the gradient of this function at 0 and at 1. Okay? And you can see that at 0, this g prime is negative, and at 1, it's positive. So what does that mean? Well, if this g of y is above the horizontal axis, this is above the y-axis here, which is horizontal. Usually we don't have the y-axis as horizontal, but in this case it is. If it's above this line, that means g of y is positive, and therefore dy dt is also positive. So that means that we're going to be moving away from it. So in this case here, sorry, we're going to be moving to the right when we're above that line, okay? So we can think of drawing arrows on this axis that will tell us the direction of change, Okay, so when g of y is above the axis, we move to the right. And when it's below the axis, we move to the left. So that tells me, for example, if I start, let's pick a point here, that tells me that I'm going to be moving to the left because my g of y is negative. Okay, so I'll keep moving to the left, and end up here. Likewise, although this is negative, let's think about this instead of being populations, let's think about this as being something like a position in space, something that could take a negative value. If we start over here, again, we're moving to the right because g of y is positive, so we're going to keep moving in this direction. So whether we start to the right or to the left of this point at when y is 0, we always end up back at y is 0. Okay, so this tells me that this is stable. And then if we compare it to the point on the right-hand side when y is 1, if we start a little bit away from it, we move to the left. On that side, on this side, we'll move to the right. So this is like my hill and valley, where this was a valley and this was a hill. When y is 0, a little bit of movement away from it, those will decay. When y is 1, when we start moving away from it, we keep moving away from it. Okay? So that tells me that the other point is unstable. So it really helps drawing these things out sometimes, but we don't have to draw things out. If we know, if we have an equation here, in this case, our g prime of y, when we substitute in our equilibria, y is 0 and y is 1, we just need to look at the sign of this function here. Okay, so regardless of what else is going on with this growth function, whatever shape it's taking, all that matters is whether it's positive or negative as it goes through the axis at our equilibrium. Okay, so we don't need to draw out these things. It can help you visualize what's going on. But all we need to do is substitute this value into our function, look at the sign. If it's negative, then that means that we have something that should, hold on a minute, what's going on here? Yes, this is stable. Sorry, I thought I'd made a mistake then. Stable and unstable. Okay, so when g prime is negative, it's stable. When g prime is positive at our equilibrium, it's unstable. Okay, have a go at the second one. A little hint for this one. You might want to multiply through by something, perhaps something involving your z to make it a little bit easier. Okay, have a go at that. I'll walk around and answer any questions you might have. Okay, can I have a show of hands who's finished that? Okay, let's see how you guys got on. Why is this question so hard? That's what I like to hear. Let's go through. Okay, so I'm going to call this my g of z this time. So you've got 1 over z squared minus 1 over z. We're told that z has to be positive here. So first thing we need to do is find our equilibria. So we need to set g of z equal to 0. So doing exactly what we did above. So when g of z is equal to 0, we have 1 over z squared minus 1 over z is equal to 0. So I said that a hint to multiply through by something. If I multiply through by z squared, then I'm just going to have 1 minus z is equal to 0. Which means z is equal to 1 is my only fixed point. So we only have one fixed point in this system. So what do I do now? I need to do my g prime of z. Before I do that, just to make sure it's clear, I'm going to rewrite my g of z as z to the minus 2 minus z to the minus 1. Okay? That's just rewriting this with negative powers. Just so it's clear, when we take our derivative, if I do g prime of z, the minus 2 comes to the front, we reduce the power by 1. So you have minus 2z to the minus 3. In the second case, the -1 comes to the front, and we had a negative there already. So we're going to get plus z, lower the power by 1 to the -2, which we can rewrite as 1 over z squared, because that's positive. I'm just switching the order of these things. So 1 over z squared minus 2 over z cubed. Okay, just a little bit neater that way. Okay, so we only have one equilibrium here. So we just need to sub in z is equal to 1. So what's our g prime at 1? We can have 1 over 1 squared. We just have 1 minus 2 over 1 cubed. So you have 1 minus 2 minus 1. So this is negative. So we already know at this point that it's stable because my g prime is negative. We could also draw this out if we wanted to. Right, I'll draw it like this. So we have our z, our g of z. We have a growth function that looks something like this. That's a terrible drawing, but it looks something like that. We know we have one equilibrium here when z is equal to 1. We know that the gradient through that point is negative for our g of z. So remember, when this green line is above the axis, we're going to be moving to the right. When it's below the axis, we move to the left. And so we can see that any small perturbation away. So imagine you're sat at this point and you nudge this ball away from there. Because the arrows, whichever way we nudge it, because the arrows point towards it, we move back. Okay, so this is stable. One thing you might have noticed whenever you're doing these systems, especially when we looked at the Allee effect ones, which we're going to do now, we're always going to alternate between stable and unstable fixed points, okay? So you can't have two stable fixed points next to each other. You can't have two unstable ones next to each other, okay? Because the stability is determined by the sign as the gradient as you cross the axis here. You can't cross the axis with a negative slope and then also cross the axis again with another negative slope. The next time has to be positive, right? So if you're doing this and you find you have a stable equilibrium next to an unstable equilibrium, you've done something wrong. Sorry, did I say that wrong? If you have a stable next to a stable, if you have an unstable next to an unstable, you've done something wrong. If you have stable next to unstable, you've done something right, probably. Okay. Let's go on to another problem, a little bit more realistic now, thinking about Allee effects. So this was mentioned a bit in the pre-lecture stuff. So Allee effects are really important from sort of conservation and harvesting perspectives, because essentially if you reduce the population below a threshold, then the population will crash. So, you know, when we're fishing wild populations, we need to make sure that we don't over-harvest them to the point where the population collapses and can't recover by itself, okay? So these Allee effects are typically modeled by modifying this term here. So this A is determining our Allee effect here. So if we got rid of this A, we end up with or rather, if we got rid of this n minus A term here, then we just have our logistic growth model. And so it's this n minus A term here that is causing our Allee effect. Okay, so we're told that all of our constants here are positives, our R, our A, and our K. N is our population size. And we want to, first of all, identify our equilibria and then classify our equilibria. Now, whenever you see classify, because I always get this question, classify an equilibria basically means, is it stable or unstable? When we go on to our systems of ODEs, things get more complicated, and classify will mean not just is it stable or unstable, but you have to determine whether it is something called a node or a spiral or a saddle. So there's an additional layer there, but classify is basically meaning tell me what is going on at that equilibrium. Is it stable, is it unstable? And for our systems of ODEs, it'd be what type of stability does it have as well? Is it a node or a spiral and so on? Okay, So we want to identify our equilibria and then classify them. So we're going to do exactly what we did above. We were going to, first of all, set this right-hand side here to just be some growth function, a g of n. To identify all equilibria, we need to set our g of n is equal to 0. And this is already nicely factored here. So we can immediately write down our equilibria because we need r times by n minus a times by 1 minus n over k times by n to be equal to 0. So whenever we're multiplying things together like this, we need at least one of these to be equal to 0. So, in fact, only one of them can be equal to 0 at a time. So that means that either this bracket has to equal 0, or this bracket has to equal 0, or this term has to equal 0. So the first bracket is only equal to 0 when n is equal to a. The second bracket is only equal to 0 when n is equal to k, because then we'll have 1 minus k over k, so 1 minus 1, which is equal to 0. And then the third term is just an n. So that has to be equal to 0. So we have 3 possible equilibria here. Okay, so now we need to classify whether each is stable or unstable. So I'll help you out with the first part here. It makes it a little bit easier if we just expand our brackets. So if I expand these brackets out, I'll save you this step. We should have an n squared minus an minus n cubed over k and a plus an squared over k. Okay, that's just expanding out our brackets to make the differentiation a little bit easier. Okay, so have a go at working out g prime of n. And then you've got your equilibria above, work out what the stability are of those equilibria. If you manage to do that as well, have a go at sketching out one of these sketches like I've done on the previous slides, where you have n versus g of n, and think about what the stability looks like if we draw those arrows on. Okay, so have a go at that. Again, I'll walk around and answer any questions. Okay, let's run through this one. So remember, we had 3 equilibria. N is equal to a, k, or 0. All of our constants here are r, a, and k are all positive. And I just expanded the brackets out here from our function above. This here is just the same as this, but expanded out. That makes the differentiation a little bit easier. So this r is just constant. We can leave it out the front. If I differentiate each of these terms in sequence, n squared is going to be 2n. I have a minus a minus 3n squared over k, and 2an over k. Okay, so just taking derivative with respect to n. And now we just substitute in each of our equilibria. So I'm going to start with n is equal to k. So what is this g prime when n is equal to k? We're going to have r times by 2k minus a minus 3k plus 2a. Notice here that we had a k on the bottom. So when we do n squared, we have k squared divided by k. So it's just going to be k. Likewise here, we had n over k. So we end up with k over k. And just cancels. Okay, so what do we end up with here now? Well, we've got a 2k minus 3k, so we're going to have a minus k. And we've got a 2a minus an a. So this gives me r times by a minus k. Now, we're told up here that a is less than k. So since a is less than k, this is going to be negative. So this equilibrium is stable. Okay, let's try g prime of 0. So now everywhere there was an n, we're just going to have 0. So these terms disappear. So all we're going to end up with is r times by minus a. A and r are both positive, so this is also negative. So n is equal to 0 is also stable. And then the last one we have is g prime of a. So here we're going to have r times by 2a minus 3a squared over k plus 2a squared over k. So this one's a little bit more complicated. We have a 2a minus an a, which is just going to be an a. We have minus 3a squared over k plus 2a squared over k, so we just have minus a squared over k. So we have r times by a, so that's the 2a minus a. And then the squared terms, we'll just have an a squared over k. So we have minus a squared over k there. We can take out a common factor of a here. This gives us ar times by 1 minus a over k. And again, we can use this fact that a is less than k, which we're told in the question up here. If a is less than k, then 1 minus a over k is always going to be positive. Okay, and the a and the r are positive, so this is also positive. This means it's unstable. So that was a little bit tricky, that part to work out. But if we had just thought about this graphically, if I zoom in here, by looking at the first two, I know that my gradient of my g is negative at 0 and at k. So I know I cross the axis at 0, a, and k, and the a is less than k. And I know my gradient here is negative. And my gradient over here is also negative. And what did I say before about crossing the axes? We can't have two negative slopes next to each other. So I know whatever's going on, I have to be crossing through here with positive slope before I come back down again. Okay, so just intuitively knowing what's going on graphically tells me that this 0 is stable, the a is unstable, and the k is stable. Okay, so there might be cases where it gets really complicated to work out the sign of the gradient, but if, say, you know what's going on either side of your fixed point, that'll tell you, you know, in this case, if we've got 3, if you know what's going on at one that is simple to work out, you'll know what's going on for the adjacent ones, because it's always going to go between stable, unstable, stable, unstable, and so on. Okay, so that graphical intuition can give you some additional insight if it's too difficult to work out algebraically. Can I have a show of hands who managed to get most of that right? Fantastic. Okay, I'm just going to run through this last example together. So this is population genetics. So here we've got 2 bacterial strains, and they're feeding on chemicals excreted by one another. Strain A feeds on chemicals produced by strain B and vice versa. So this is known as cross-feeding, happens quite a lot in bacterial populations. And we're told that suppose that 2 strains of bacteria are engaged in cross-feeding, strains 1 and 2. And for a relatively simple model, the frequency, P of T, of strain 1 is governed by this differential equation here. Now, in many ways, this is actually a system of differential equations. We could split this into strain 1 and strain 2 and have a population model for each of them. But since we're just interested in the frequency, we know that the frequency is always going to go between 0 and 1. Okay, so we don't have to model both of these populations. We can actually just collapse it down to just a single model where we look at the frequency of one of the strains. So if the frequency of strain 1 is P, the frequency of strain 2 is going to be 1 minus P. Okay, so we have this model here. Alpha and beta are positive constants, and we're given some values for them. Alpha is 1, beta is 2. Okay, so it asks us first of all to simplify this differential equation. So this is just a case of substituting in my alpha and beta. So we have dp dt is going to be P times by 1 minus P times by alpha, which we're told to be 1. So 1 times by 1 minus P minus 2 times 5p. So beta is 2. So if you simplify this out, we're still going to have our p and 1 minus p at the front. Then inside the bracket, we're going to end up with a 1 minus 3p. And I'm going to call this my new growth function g of p. Okay, so now we're asked to find all of the equilibria. So that's just when this growth function is equal to 0. So why do we need this to be equal to 0? So p is equal to 0, or 1 minus p is equal to 0, or 1 minus 3p is equal to 0. We need p times by 1 minus p times by 1 minus 3p to be equal to 0. So just like before, we can immediately write this down. Either p is equal to 0, or p must equal to 1 from this second bracket here, or from the first bracket, the second term. Or 1 minus 3p is equal to 0, so p must equal a third. Okay. So how about the stability of these different equilibria? Just like above, we can expand the brackets out. So this is just a bit of algebra, so I'll just write down what the answer is. So p minus 3p squared minus p squared plus 3p cubed. Yeah, this is just expanding out those previous brackets. Don't really need to worry too much about this because that's just a bit of algebra. P minus 4p squared plus 3p cubed when it's simplified. Okay. What we really care about here is thinking about the derivative of this function. So what's g prime of p? That's taking the derivative of this thing over here. Okay, derivative of p with respect to p, you get 1. Minus 4p squared becomes 8p. And 3p cubed becomes 9p squared. So differentiate with respect to p. Now we need to do is substitute in those equilibria. So p is equal to 0, p is equal to a third, or p is equal to 1. So when we have 0, we're going to have 1 minus 0 minus 0 is 1, which is positive. So we know that p is equal to 0 is going to be unstable. At this point, because as soon as we've worked out one of them, and because they alternate, we actually know all of them, but let's go through them for completeness. When p is a third, we're going to have 1 minus 8 thirds plus 9 p squared. So p squared is a third. Sorry, p is a third. So p squared, we're going to have 1 over 3 squared. So that's going to work out quite nicely. On the last line, g prime of 1 is equal to 1 minus 8 plus 9, which is going to be positive. So p is equal to 1 is unstable. Like I said, as soon as we've actually worked out one of them, we didn't need to work out all of them because we know that they're going to alternate stability. Okay. So what does this actually look like? If we plot our p versus our g of p, this is just like our Allee effect above, but now with everything flipped around. So we actually have g of p as a cubic, and we know that it crosses the axis at 0, a third, and 1. And we knew from the first one, when g prime of 0, we looked at that, that was unstable. Our gradient was positive, which means that we move to the right here, the left here, the left here, and the right here. So remember, when that green curve is above the axis, we move to the right. When it's below the axis, we move to the left. So that means that this is unstable, this is stable, and this is unstable. Okay, so what does this mean biologically? Remember, this problem is all about 2 bacterial species that are cross-feeding. What happens if we just chuck them in at whatever frequencies? Well, we can see that they both will eventually tend towards an equilibrium, where strain 1 is at a frequency of a third, which means strain 2 is at the frequency of 2/3. Okay, so there should be twice as much of strain 2 as there is strain 1. Okay, I'll correct that mistake in the solutions and post it online. Thanks, everyone.